I think I'm supposed to start at 9:10. So we'll get going on that then. One of the things, so as a result of some conversations with other people and also with some of the committee members that live in my head sometimes, I think I want to reemphasize. If I didn't emphasize it earlier, I want to reemphasize some things for some of the younger people here. That one of my goals in these lectures is this is a sort of invitation to research, if you will. I want to present. I want to present some areas where there are some things to be done, maybe. On the other hand, I also seem to be presenting a lot of warnings or indications of serious roadblocks to some of these things. And I'll be talking more about some of those today. So I was maybe going to wait till later, but one of the things, that let me just reiterate that one of the things we do know is that at the moment, if we have R here, this is say minimal expansion of the field, and so it's a field of exponents Q, so it defines no irrational power functions. Actually, I want to change this one. Let's go back to, this will be we want restricted x and restricted sign to live here. So say on 0, 1, I think is the usual one. We'll do, so this guarantees that all compact trajectories of linear vector fields are living here. We can do that. All right, so these are the guys we've been looking at. And then if alpha is bigger than 1, then if we put all these guys together, then this thing, the expansion here by predicate for the group, is known to be well behaved at a certain, in certain ways by model theory. It's known to be well behaved and to define a log spiral associated to the group. Some log spiral. So the logs, I should say the log spiral associated with the group. So in other words, the log, this is the intersection of the log spiral with the positive axis. So this is known. This is aside from omnimality of when we're looking at expansions by trajectories of definable vector fields. In here, this is the one arena that we know of is nice. We know lots and lots of stuff. We know model theoretically. We know how this is axiomatized relative to the theory of this. We know what the definable sets look like in here relative to this and the group. And so this is known. What we don't know is that is there anything that we could think of as tame behavior that's either not O-minimal or not one of these guys when we're thinking about control theoretic things. That is what's sort of open, and that's where a lot of the impediments are. However, I think it's, I should point out, lots of people know this for like 25 years or something. People have been taking O-minimal expansions of the field of reals and taking results from semi-algebraic and subanalytic geometry and O-minimalizing them. So okay, fine, we know that certain results hold in certain settings, and we're just going to O-minimalize them. And this is sort of an industry for quite a while, and you can crank out a lot of papers doing this, and I think some people are still trying to do it, but that well is getting a little dry, frankly. So this is an area where people haven't done very much. So I guess that's one of the things I wanted to get out front here, is that I'm really not, I'm not trying to encourage people, not trying to necessarily discourage either, but some of these open problems I'm mentioning in the other direction, like saying what other kinds of tameness are there when dealing with these control theoretic issues. A lot of people have worked on these kinds of things for a long time. A lot of them ultimately boil down to questions in either ODE theory or definability theory that we just don't know. Okay, so, but there are areas here where things can be done. I don't, there are a lot of good things about these particular structures. I don't want to go get too much into that now. I was going to reserve that for later. But again, I just, you know, yes, I think there is work to be done here. There are results that can be obtained. For example, you know, analyzing sort of tame control theory inside of these structures. That's something that's doable. Some of these other things I'm going to raise, maybe not so much. I realized yesterday we were doing the question period that even for the famous structure R sub n, we, as far as I know, we still don't know whether all compact trajectories of definable vector fields in that structure, say C1 vector fields, whether they live there. We don't know that. We know that all analytic, yes, but there you don't even need definable. If you have an analytic vector field in the compact trajectory, it lives in Rn by definition, well, almost by definition of Rn. But even there we don't, now I think that's possibly doable, that one, but I don't know how to do it yet. So with I wanted to clear the air a little bit about some of this stuff. And along the same lines here, because some of you...
Sorry, wouldn't the C1 trajectory value be analytic almost everywhere?
Yes, almost everywhere. Yes, that's right. How do they join together? And that's where you're not compact necessarily. And this is maybe this is easily done. I tried to. You could rephrase this actually by saying if you have a compact trajectory of a subanalytic vector field in Rn or in Rn space, and you have a compact trajectory, is the compact trajectory necessarily subanalytic? That can be rephrased without any definability at all. I thought this should somehow be obvious, but when I tried to do it, well, I couldn't. So there's still lots of stuff to do here. And I also wanted to mention here, because some of you might have run across some of this other stuff before. You're saying, well, wait a minute, Miller, we know there's other things that are a little bit like this that also have a good model theory and that we understand. So yes, there are things like, it's also true. Just to take an example, that's something like, we can look at this thing, say, to allow the notation here for alpha beta greater than 1, say you could take alpha equal beta equal 2. So instead of, say, the integer powers of 2, you could be looking at the 2 to the 2 to the n's. You could also be looking at something like the sequence n factorial factorials. I'm abusing notation a little bit. And yes, we know that we know how to, we understand the model theory of this thing relative to this one. We know lots of other things. We understand the definable sets. There's this notion of de-minimality, which I have always warned people I didn't think was robust enough to warrant abstract investigation. Yes, there are these other objects. The thing is, I see no evidence whatsoever, and I see plenty of evidence that these things are not going to come up naturally as these are not going to come up with as intersections of trajectories of vector fields. They're not right. They're not right. You could probably concoct by hand some weird trajectories that, I don't know, I'm flattening it out to keep it on the board, that are this spread out, but they're not going to be natural. I don't know how any of them show up. They're not going to be trajectories of vector fields. So I'm definitely keeping this whole enterprise restricted to expansions by trajectories of definable vector fields. These things, who knows? I mean, I don't think they're going to show up. A concrete way to get some research done and get some mileage out of this is to simply prove me wrong. My rough conjecture is that there's no other arena of tameness besides these guys when you're expanding this kind of structure by trajectories of definable vector fields. There's omnimality, of which there's been lots of work, and there's this. That's my gut feeling. This is the only other place where there's going to be any kind of reasonable tameness for expansions by trajectories of vector fields. Yeah, there's these other things. They're useful as examples or counterexamples to certain things. I don't know if they really have any great content to them mathematically. All right, so there's a big long disclaimer. Watch out for, yeah, I think there's stuff here that can be done, but you have to be careful. Okay, so first, this order of business here today is what I was calling this fundamental alternative. And we'll talk about proof of this a bit today. It's easier to draw this as a picture. And it's true here that here I'm only assuming, we only need to assume omnimality to get this one to work. It's not these guys, but again, eventually this is what we care about, are these kind of things. So here we're just going to say we have F is say F1, F2. This is going from, I'll just say R squared to R, but let's say C1 in a neighborhood of the origin. Just because actually locally Lipschitz is certainly enough, I think, but C1 is easier to say. Now, so here we have a vector field. Let's say we have an isolated. We want to say that the zero is just going to be the origin, and I'm going to stop writing 0, 0, I guess. So we have an isolated singularity. The vector field is vanishing here. Now it's actually a sort of trichotomous statement, but one of them is goofy. We could certainly have, so now we want to have, say, some, let me go ahead and say we have a parameterization. I'm going to make this, in order to make the notation easy, we'll make it total. We'll have this, we'll have, this is differentiable. It'll be a solution. There, okay. And so we know already that all the compact pieces of this thing are fine. We don't have to worry about them. So the question is, what happens as we go to plus or minus infinity on here? Now, it certainly could be that this thing doesn't go anywhere, doesn't go to the origin. It could be a closed trajectory. All right, so that's certainly a possibility. That the origin's just not in the frontier of the image. Okay, so I want that. All right, so that's not the interesting one. So basically what makes this, you have to assume that you actually have something that goes to the origin to make this at all interesting. So we'll assume that the origin is in the frontier of the trajectory. And let's remember, this is not the boundary, this is the closure of the set minus the set. set minus what you started with. All right, so then only two things can happen. And pictorially, either you have to come in like this on some definite thing like this, and the picture already suggests that this is going to be Pfaffian over what we started with. And so if I cut off and have any half trajectory, this is in fact going to be definable in the Pfaffian closure. So it'll happily live in this big O minimal structure with other things. That's one possibility. And the other possibility is that you have to spiral. Now, making that precise is kind of a bit of a pain at times, and this has to keep going. Okay, so either you spiral or you have to come in on a definite direction and settle down. And in fact, then you'll be Pfaffian over the structure that you started with. Now, if this happens, then it's just a fact of basic ODE theory that then every trajectory has to do that nearby, because the directions here are the same. So you can't, there's no way to squeeze, you can't make any funny trajectories do anything in here. So all the other trajectories would be in here, and you wouldn't be O minimal for, or anything like that. At some point now, though, we'll have to be wondering, how much does this look like a log spiral? And how much doesn't? So, but these are the two possibilities here. And if you have an analytic vector field, this is an old result. So if this were, instead of C1, if this were analytic at the origin, then you can find this result in pretty much lots of books on ODE theory. Now, this is really important. And I'll say, at the moment, we're not worried about what the entire phase portrait nearby looks like, but this is going to come up and be an issue too. All right, so now I should, oh yes, in the analytic case, there's also there's better information, there's more information that you can have. You have a complete, you can classify all the possible phase portraits. You can say something about what these directions are like based on some of the content of what you can read off the power series. For example, if the linear part is actually not zero, then these directions can be read off from eigenvalues and a little bit of algebra. Now, we're not going to be able to do that so much in this abstract setting. This is just going to be a purely O minimal argument as to how this works. But we see even from here, so you say, well, why should this be important? Certainly in ODE theory, the way it's developed almost always is first you look at linear vector fields and you try to understand them as well as you possibly can. The next thing is to look at the behavior of things with isolated zeros and look at the behavior in the neighborhood of an isolated zero. Are there more complicated singularities? Yes. But this is the next thing that people look at, is this isolated singularity case, which can always be translated to the origin. So in terms of the program that we're getting after, now, so basically if this happens, well, you certainly can't also have this. So that means if I take any other trajectory of the same vector field that goes to the origin, it's also going to have to wind up with a definite direction. and that's going to be Pfaffian over the structure. And so all of, you can, and this is supposed to indicate that we're dealing with a half of a trajectory here, half maximal. Okay, half maximal. So basically, you can add all of these things, and they all live happily in one big O minimal structure.
Uniformly? You can add them uniformly?
It depends on what you mean by uniformly.
You have a definable family in the Pfaffian closure with all of them?
If it's a definable, I'm not sure we actually know that, which by the way reminds me there was something else I have to talk about too, in terms of doing some backfill on this. So I'll have to try to keep that in mind for a second. By the way, of course, there are other pictures we could have here. There are other pictures we could have. So, and in ordinary, in the usual analysis of qualitative ODEs, people really care about these things. When are you leaving? When are you coming in? What do all the pictures look like? So another possibility that you can have here is something like this. You can be coming out and then come back. This is called an elliptic trajectory or something. So we don't care about this. There's a half trajectory. There's a half trajectory. We both throw them in, everything is fine. Even if we didn't want or cut them there, there's a compact piece. Okay, we know we can worry about that. So these are really, over here, we're really thinking about germ behavior, but at the same time, we have to actually think about definable sets. So no matter where I cut these guys, this might keep going out, but as long as I cut off a piece of it, it's kind of like extending what we know about the compact trajectories in the Pfaffian setting to some non-compact ones. Okay, that's kind of what this is about. But the thing is, you can also have other pictures where you have you could have some, well, we've said there's only an isolated singularity at the origin, but you could have other things where you have some good behavior here, and then some kind of crazy behavior over here or something. But it doesn't matter how bad things are over there, as long as we cut off the half trajectories, because we're still going to be able to use this together with that the compact trajectories are okay. So we're not going to concern ourselves with trying to recreate and analyze all the classical work on what these phase portraits look like. All we care about is whether we spiral, and then we're not going to be O minimal, or in this case, where we can add all of these guys. There could be, yes, I should also say, there could be other trajectories that do stuff like this, that stay away from the origin altogether. It's the same vector field. We know we could take any compact pieces of that and throw it in, and we're still good. So again, not worrying about what the whole phase portrait is. Okay, let me partially respond to Kobe's comment. Yes, it's natural for us to want to think about definable families, the flow of a vector. It's natural for us to want to think about not just one trajectory at a time, but the families of them, and ask questions about, okay, what happens if I add, you know, these what's so-called the flows nearby. Okay, now here I'm really insisting that we need to walk before we can run, and we need to crawl before we can walk. My point of view at the moment is that first we need to make sure that the individual trajectories don't define the integers. Once the individual trajectories we know are all okay, and then we have a big collection of them that are jointly okay, then we can think about whether we can add phase portraits and so on. I think I did mention in an earlier lecture, in this structure here, as long as we've got these things, and we're assuming we've got them, then the basically the restriction of complex exponentiation to any bounded box or disk or whatever you like is going to be definable. You have restricted x, you have restricted sign. You can get then you can get this as big as you want, which also means that more generally you can get the exponential map that shows up in ODE theory. So then yes, you can certainly get as big a chunk of the flow of, actually, if you fix an n, you can get big chunks of the flow of the family of all linear vector fields, more or less. Because if you have finitely many vector fields, you can always gang them up into one. I mean, usually when you analyze them, you do the opposite. You want to do matrix operations on them so that you can deal with them in chunks. But you can always take finitely many vector fields, linear vector fields, turn them into one big one. And then in there, you will simply have, you'll have all of the solutions for arbitrarily large finite pieces. So yes, so that's the thing. We know that sometimes you can add big chunks of the flow. We know that sometimes you can't. And then so part of the game there can be to try to determine, well, what situation are we in and when? Okay. So, but for now, let's just get to, because you see, my interest at the moment is actually not so much in this one, where we wind up in this Pfaffian and no minimal case. My interest is more when we wind up with the spiraling trajectories. I know in some cases we define the integers. I know in some cases we wind up in this, log spirals. I'm not sure exactly what else happens. That's what needs to be cleared up. However, it is perhaps, I think, also the kind of thing that you observe if you're reading ODE literature. Log spirals show up all the time. They show up naturally. They show up as natural. They show up to solutions of, say, even applied problems. I think, in fact, somebody, I'm not sure, somebody told me, I think it was some, all right, it might have been a math biologist. I can't remember. Someone told me, for example, that birds of prey, when they're circling down to the projection of their path is a log spiral. It's the most efficient way for them to spiral down and hit something. Of course, sometimes they see the bunny and just, hit it like that. But if they have to come down, they come down on log spirals. So log spirals show up all the time. They're indispensable. They're indispensable theoretically. They're indispensable for applications. On the other hand, these other spirals that we can create these things by hand, and they will define the natural numbers. But they're in ways that can be made precise. They actually don't show up, so they are kind of unnatural. And at some point, I'll be talking a lot more about what should we do with this case, because this case we kind of more or less understand. At least this case then becomes more questions about O-minimal ODE theory. So okay, that goes over in that box. Fine, more O-minimal ODE theory. Good, go for it. This is the other direction. This is the one I'm interested in more at the moment. All right, so let's start talking about how to deal with this, the proof of this theorem. So I'm going to give a heuristic here that I use to help me remember calculus I probably learned, I don't know, 40 years ago, who knows. If you're not teaching calculus all the time, you can forget these things. So I want to, the classical analysis of how to get this result is you usually do this by passing the polar coordinates. Now that's great, but we can't really do polar coordinates definably in these structures. If you need the angle to be unbounded, well, we can't, and you do with spirals, all we have is restricted sign. So we can't really do polar coordinates, definably, but we can use, we can do some definable things that will help us avoid actually using polar coordinates definably. So here's a little heuristic of mine for this. So I like to use some complex analysis here. So if I take my path and write it, and I'm already assuming that I have some nice way of doing this. I mean, we know what this has to be. This has to be this has to be the modulus here. But this thing is sometimes a little mysterious, but we're just assuming that we know that we have it and it's differentiable in C1 and all this. So if we just do a little logarithmic differentiation here in the complex world, not in the real world, what we wind up with is we get rho prime over rho plus I theta prime. Okay, so this, of course, is the derivative of the log of the distance, which makes sense because when you think of the complex numbers as a multiplicative group, the complex plane minus the origin, the real distance is logarithmic. The actual distance of the origin, if you're thinking of it as a multiplicative group, you really should measure logarithmic distance to the origin, so that when you're on the unit circle, the distance is 0. That's where your origin is, so to speak. All right. But anyway, so that's this here. And this would, of course, be the derivative of the angle. So in theory, if I integrated the imaginary part of this thing, then I'll be integrating the derivative of the angle, and then I can actually recover theta as in pure polar coordinates, not just as, well, what is it, capital arg, where you restrict the, where you have to restrict the value, where you have to use restricted sign. All right, so if I use this here, this just helps me remember some things. So, but of course, gamma prime in our setting is really f of gamma. So now what I have is f of gamma over gamma is equal to this thing. Again, this we have a concrete expression for, but this is not so clear. All right, so because these guys are equal, so now I'm looking at this, and now I just substitute z's in for here, and because I'm going to have to work with rectangular coordinates, so that's what I'm going to do. Okay, so this is, again, this is all heuristic. I'm not claiming this is a proof of anything, but this leads me to look at this, which is then going to be c squared. And now this I can certainly express in rectangular coordinates. So if we go ahead, well, I'll skip a little bit of the computations here. And what we wind up with getting here is that if I go back to thinking about this as in two variables, So now I'm switching back, back to R squared now. And I'm getting these expressions. Now, I can never memorize these because I don't use them on a daily basis and I don't teach it on a daily basis, but I can always remember this process. So this is the way when I have to remember how this works, this is what I do. Okay, so what good is this? It means that if my trajectory, if I then put the trajectory back in here, so now gamma 1, F2 of gamma, gamma 2 of F1, and so on. What I'm getting here is the derivative. I'm getting the angular derivative here. Okay. This I'm not going to use as much for various reasons, but this we need. This is now like if we stuff gamma into here, we're getting its angular derivative. So why is that useful? Okay, well, certainly, in fact, I might as well hold on to all of these guys. We can certainly look at the following sets. Actually, let's get that out of the shadow a little bit more. Now these guys are certainly definable because the vector field is definable. And of course, this is really shorthand for the three sets where I'm strictly greater than 0, equals 0, less than 0, and so on. So this is how I get away from actually having to use real polar coordinates. These things are certainly all definable sets from F. And if my trajectory is living in this set, then the angle, we have to be going counterclockwise. If I'm in this one, then we have to be going clockwise. If I'm here, well, we got to be a little bit careful, but we don't think that should happen too often. Oh, sorry. This is for the derivative. This one says we're either going in or we're going out or we're staying about the same on the distance. This is the one that says that if I'm greater than 0, I have to be moving counterclockwise and so on. So this is the one that we're going to be most interested in this argument. But you can sort of see that if I'm in a no minimal structure, I can say take cell decomposition that respects all of these sets, and I've got a pretty good idea of how my trajectory is going to be behaving as it when it's living in these sets, I pretty much know what's going on. So then all I have to somehow try to do is to figure out what happens when it's leaving one and going to another. And this is the key trick from the way I see it to these arguments. All right, so I'll be doing, there's a bunch of calculus behind this, and yes, I learned an important saying from someone who was on this very stage 25 years ago. They said, never differentiate in public. This was Sergei Yakovenko. So I'm not going to try to do the calculus because you have to be careful with calculus, and some things are best done in the privacy of one's home. Okay, so but let's just think about this for a minute. We don't even need to think about the O minimality too much at the moment, but just suppose that my setup is that, say I've got a neighborhood of the origin where this condition is holding. All right, so so I could have a ball around the origin where I always have this holding. And I might as well even, to make it, if you want to really sort of get a picture of why this is measuring what it's measuring, we have this. And so if you start trying to draw the pictures and rise over runs and all those things, this does indicate that you have to be moving this way. All right, so suppose that I've got this condition on a whole neighborhood of the origin. Okay, so it's positive. And then dividing out by the norm certainly doesn't make any difference. And if my trajectory, remember, my trajectory never touches the origin, it just goes near it. So I can actually reconstruct what the angle is here. So I'm going along, say, I have an individual trajectory now, and who knows what it's doing around here, but eventually, let's say it gets in here. It's in here, and now it has to start spinning. So what this means is that I can find some A where I start looking at this guy. So rats. I was going to give this a name, but oh well. So now I'll just have to be careful about it. Gamma 1 times this minus gamma 2 over F1 of F1, oops, F1 of gamma. And this is something I forgot to put in a paper by the, so we have this on the bottom. All right, so this now is supposed to actually be the angular derivative. It's strictly positive in this whole ball. So I know what I'm doing here is I'm getting an increasing function, positive, increasing positive function. So when I let t go off to infinity, I either get plus infinity or I wind up with a finite number. So this integral will exist. So we're just going to integrate. We're basically thinking about integrating the angular derivative, which we know is being nice. And there's, again, we get two possibilities. Either when I let this go to infinity, I have infinity, positive infinity, or we approach a finite number. So if it's positive infinity, what does that mean? That means that I keep having to accumulate more and more angle. So we have to have a spiral. In fact, it's not easy to define what a spiral is purely geometrically. If you look at in a note, what people mean, they say, what is the definition of a spiral? It's usually, you actually have to say something like, well, okay, what I really mean is we have a set that's parametrized by something that looks like this, where this is continuous and this is continuous. You can also start throwing other things on it, but then you can say, well, this has to go to either plus or minus infinity, and say this would have to go to 0. So almost by definition, if this is plus infinity, we have to get a spiral. Okay, so this has nothing to do with, so this part, if in fact I was lucky enough to have this condition holding in a neighborhood of the origin, so what happens if it approaches a finite number? That means this angle is approaching a finite number, which means that the e to the I theta has to be approaching a unit vector. And so in that case, what's the picture that we have to get? Well, let's see, I'm not as good at drawing this one, but so in that case, there has to be a unit vector somewhere and a direction. And let's say because we're going counterclockwise, we have to be coming, but we also have to be going to the origin, and we have to go to the origin. And basically, we wind up having to do something like this. Now you say, well, wait a minute, couldn't it wobble across? No, because the angular derivative would have to change again. You can't quite do that under any reasonable circumstances. So in that case, the only possible picture that you can get out of this is you've been spinning and you're coming, but eventually you have to go to zero, because that is part of the assumption here. The trajectory is going to zero. And so then you wind up with this kind of picture. And if we're doing this over a no minimal structure, then we do some standard arguments to show that this would have to be Pfaffian over the original structure. Hence, you can add it and preserve O minimality. Okay, so, but now this is the argument if we have this condition holding in a neighborhood of the origin. Okay, with a little bit more fidgeting, not much though. In fact, I didn't really need strict inequality here. I could have greater than or equal to. This thing will still be accumulating. This will still be increasing, maybe not strictly increasing all the time, but this will still be increasing, and we can still do, the argument still works if you're just greater than or equal to zero in a neighborhood. Okay, so that's something that could be checked. Now, of course, similarly, then we could go on and say if we're less than or equal to zero, if this is happening in a whole neighborhood, then we're going to get the same argument, except in that case, now we have to do everything clockwise. Okay, so these two cases, we get the right pictures that we want right away, even without invoking any analyticity or O minimality. The only place that comes in at that point is that we do want to argue that in this case, we get a Pfaffian set that we can apply Pfaffian closure to. All right, and that's not a hard argument. Okay, so that takes care of those cases. But then, so what's left? What's left is the case that that every time we look at a neighborhood of the origin and shrink it down, there's going to be some places where this is strictly positive and some places where it's strictly negative. Now we're going to start using some O minimality. And this is one of these things where there's an expression I love to. I have to teach a proofwriting class a lot at where I work. And there's an expression I picked up somewhere that I like, and it's the proof does not convince, and that which convinces is not a proof. I always like to tell the students this when you're teaching them basic set theory proofs, because like when you want to show the Venn diagram for how to A union B is A intersect, you draw the picture and everybody is convinced, and then you try to actually teach them how to write it down in our accepted format, and that certainly doesn't convince them, and it takes them a while before they can learn how to do it, if ever. So in this case, yeah, we could write all these details out, but really the pictures here are what are going to convince us that this is true. And then you have to check the details and try to write them up without making dumb mistakes. That's the hard part. All right, so let me just quickly sketch how the other thing works here by picture. And we should be able to, so this other possibility is that every neighborhood of the origin contains places where you're greater than zero or less than zero. By the way, you can't, if you're always equal to zero, then you're just coming in on lines. That's not very interesting. You have to have the vector field that's just line, where the trajectories are just lines to the origin. Okay, so let's go ahead and take a cell decomposition of this guy, and the picture that we're going to wind up getting, something like this. There's my singularity, and I'll have regions where, say here I'm going this direction, and let's just say if here I'm going this direction, then this certainly suggests that certain things are, I can't actually cross from here transversely into here. So if I was in here and trapped, I'm going to actually have to come to something, and that's going to be Pfaffian. If my trajectory it has to stay in the interior. If it's in this case, it can't cross the line because my velocity is supposed to be going this way, and then if I went over, I was supposed to be going that way. Okay, so that can't happen. The other thing that could happen is that you say, well, what if I'm so this is a C1 cell. That's one of these boundaries. Now we can do this either geometrically, or we can use it by the way that we know we can parameterize by curve selection. We could parameterize this thing itself as a map, I don't know, call it theta or something, where this parameterizes coming into here on an interval up to infinity. Why do we care about that? Because then I can easily check when is this going to, we can take it to be C1. So we can look at the set of points where this is true. We can look at the set of time points where this thing, regarded as a curve, actually satisfies the differential equation for the vector field. Aha. Well, that means, because rho minimal, that either this has to hold on a whole interval, in which case I'm a trajectory. So, trajectories can't intersect. So this would be a boundary of one. Or the other thing is that we always have to be of some constant sign. So in this case, we can't be transverse to this thing. We would have to be coming this way. That can't happen if this is the picture. And so I had to have been, this has to be a trajectory here. And then anything in here has to do something like this. Or, well, I mean, it could just, oh no, it can't do that. Okay. Now, okay, so that's if this one happens, but we could also have, let's say,
would it have to be linear actually in this thing? If the boundary is a solution, would it have to be zero then, and then it will have to be linear?
Linear. I don't think that's quite necessary. We can check that.
All right.
But so this is one, I deliberately drew this one so we can just sort of see this geometric argument about sort of headbutting, right? I can't cross this line if this is happening over here. But of course, now you could have them two together where I'm crossing here and into an area where the angle is also going this way. And in this case, what has to happen is that either this winds up being, again, well, I'm getting a little bit ahead of myself. If it's not this, if this is not actually a trajectory, then basically we have to be always crossing transversely in this direction. Okay. Well, you can keep going with this argument and you can still see that you can wind up with spirals. But basically, these kinds of arguments give us everything we need, give us the result. We just have to be, patient and careful and draw them out. So I don't want to beat us over the head with details on this stuff. This is the key point, is that these sets are definable and we can decompose them. We can also, for that matter, we can also decompose the zeros of F1, the zeros of F2, any data that we think is relevant here. You can decompose all of this stuff. You get pictures that all you need to do is find the calculus computations to then verify what the pictures mean. That's actually how the proof works. Again, this is not a proof, but I hope it convinces. And the proof itself, well, I wrote it up once. Yeah, I guess it's not as convincing as the pictures, I think.
The only way to have spiral is actually the neighborhood greater or equal to 0 or less than or equal to 0 cover the neighborhood of the origin?
Yeah, I think that's right. Now, by the way, okay, now there's some really strange there, because we're allowing just C1 things here, there are some weird things that can happen, but they would still count as spirals. There are some strange things that could happen. Let me just, I have a hard time drawing them sometimes because they're a little weird. If you were an analytic vector field, then the places where these where the angular derivative is 0 has to be very thin, right? You can't have interior because then you would well, you could, but then you're just this trivial vector field where the trajectories are just lines to the origin. I guess if you have a C1 vector field, I suppose it's I once learned how to do this. Let me see if I can remember. So say I could be coming this way and then dive straight to the origin for a while and then hit something else and resume my track. Yep. Something like this. And if you draw these some cuspy things or something, is that the right? No, it would have to go the other way because we're going counterclockwise. No, something like this. Yeah. Sorry, I'm not good at drawing these. The point is, it would be possible if you just have a C1 vector field to have a situation where your angle is really going somewhere, and then you take a dive straight down to the origin, but then you run out of that again, and then you have to pick it up again, and you go around, and some strange things like this can happen. But it's still a spiral in the abstract sense, according to the definition. So
It's greater or equal to 0.
it would, you basically, you can have open regions where it's actually equal, where the angular derivative is actually equal to 0. So it makes it dive into the origin for a little while, but then it'll hit the boundary, and then it can cross and start going back around again. These can't happen with analytic vector fields or C infinity vector fields in the polynomially bounded case. But I didn't see a reason to rule them out because they still count as spirals. Questions? Comments? I know somebody who needs a break. That's me. 5 minutes. All right.
like this proof like picture. It's so much more informative.
When I first really started getting interested in this stuff, I would look at these books on these classifications of analytic vector fields, and I would say, okay, here's a picture, here's a picture, here's a picture. You just look at it and you say, well, those are Faffian, right? Obviously, you know, and then so then all you have to do is sit down and okay, do some calculus to you know, to actually verify it. You know, so at least for me, it was the pictures that motivated all the thoughts behind it. Anyway. Yeah. Also, I should also give a nod to Polanski. The first time I saw him speak here when I was I think a postdoc. Yeah, I'm still. And he was up on the stage, and you know, he came up and he was pacing back and forth, and I think so he did something like basically drew a picture of the coach and he died. Then he said, rest is detail.
Divide and conquer.
You know, and I remember the first time thinking, that's pretty cheap. But he was right, you know. The rest is detail. So,
The Arnold school.
the Arnold is certainly one of the things I learned. Yeah, that I did pick up from them is that okay, first you learn pretty much everything you can about the best possible. First level of trouble, the first level of singularity. And that was completely the opposite, I think, of the way of like American training of math majors. You know, you immediately start, oh, let's look at this Cantor set, or you know, look at this weird thing, look at that weird thing. It was only when I was a postdoc that I started realizing how little graphic math I knew, and had to fix a lot of that, especially when you're doing this kind of stuff. There was a lot of backfilling. Okay, I think I get
Off. So, are we back on? Okay. Very good. Okay, so yeah, so now we have this thing called this fundamental alternative. This works in completely arbitrary O-minimal structures. You know, you could have flat vector fields, you could have all kinds of stuff that we would never look at, but it always works. It always works, and it's based on these pretty easy pictures. Now, just to actually, I was saying this to someone during the break here anyway, in the analytic case, not only do we have sort of quantitative, you can read off from power series expansions where these things called separatrices, I think, yes. And a lot of work is done where you actually fill in the whole phase portrait. You say you can have, these things called saddle nodes, this, that, and the other. And for me, this was when I saw these pictures early on, and you just look at them and go, okay, well, those all have to be Pfaffian, and so those should all be good. And then there's these other things called spirals, and those are obviously not O-minimal, and some of them are okay. It later turned out, and some aren't. But so it's very tempting to think that, another black box fact I have to bring out, that in polynomially bounded O-minimal structures, C infinity functions act essentially like analytic functions in the sense that they form quasi-analytic classes. So if you have a C infinity function at the origin and you look at its Taylor series there, no other definable function can have that Taylor series. So it's really tempting to think that, okay, then all this classical stuff about analytic vector fields, this should all be true for C infinity vector fields in polynomially bounded O-minimal structures. But there's a problem there. And I wanted to, and I have to bring this up. So we've been, one of the assumptions of this fundamental alternative thingy, this dichotomy, one of the assumptions is that we were looking at a trajectory that went to the origin. Well, maybe you don't have any. That's certainly possible. You can take just the, let's see, what is it? The standard vector field that just gives you circles. The trajectories are just circles through the origin. Let's see, well, we know what that's supposed to be. There's supposed to be cosine t, sine t, so we can reconstruct the vector field that gives us those. So that's a possibility, is that you can just have all circles around here, or, you know, ellipses and, or, you know, various things. But you can have, it can be the case that around your singularity, every trajectory is a closed thing like this. Okay, that's certainly possible. And so then you think, well, yeah, what else could go wrong? But it can go wrong. So I need to give myself a little more room in there. In vector field theory, where your singularity is surrounded by closed trajectories like that, it's usually called a center. Okay. If you have a point where your things are spiraling in or spiraling out, that's called a focus. Okay, so you have centers, you have focuses. Then there's a bunch of other things. You can have saddle nodes, a bunch of other things. Now, unfortunately, there's another possibility, and that's what's called a center focus. Usually hyphenated, I suppose, or maybe not, but I think I've even seen some people run it into one word. Center focus is where you have a family of circles coming into the origin, but these are isolated in the closed, there's no other closed trajectories nearby. And what happens in between is that you have spirally stuff. And depending on the direction of, you know, you can have it where everything is going in the same direction. I don't care about directions, but, or you can have it where these go in opposite, and you, let's see, is that right? You spiral out that way and then spiral in this way. I guess that's, yeah. However you're forced to draw the picture, but you can have rings of closed trajectories that are each filled in with spirals that go all the way to this one and all the way out to this one. Such a thing is called a center focus.
But then these cycles become arbitrarily close to the origin, right?
Yes.
Close. Okay.
Yes, and so this is exactly this is another way where no trajectories go to the origin. Instead, what you have closed trajectories like this abstractly, and then you have spirals that instead of spiraling just around a point, they spiral around a closed trajectory. So nothing here, no trajectories actually go to the origin, and there's no neighborhood of the origin where you can escape this fate. So no matter where you look, this fundamental alternative, well, it's an entirely different kind of picture that you get with these. Now, okay, so can't happen with analytic vector fields. Okay, these guys, this situation cannot happen if you have an analytic vector field. Now that should be easy, right? Unfortunately, no. This is certainly when I first started hearing about it. Right. Okay, so why is this true for analytic vector fields? This is we have to talk about return maps. And what's so more generally, anytime we're dealing with a sort of spiraling situation or anything like that, we have something called the Poincare Return Map, or sometimes first return or whatever, but we'll just call it the return map. And let me just, for now, use a spiral because it's easier to illustrate how to, again, by picture, we're going to do this. So suppose I got a spiral, I've got something going on like this. All right. Now, the picture makes it pretty clear that, now remember, all the trajectories have to be doing this as well in this neighborhood, because if we're having a spiraling trajectory, then they all have to do it. So you throw me a point that's on, say, in this case, the positive real line. Give me a point here. There has to be, by existence theorems for differential equations, there has to be a trajectory that goes through that point. It's going to have to spiral. This is ODE theory. So has to be a trajectory that I'm on, and I have to come around, or the other way. But you have, so this comes around, and obviously, according to this picture, it hits the axis again. Fairly, and so we get actually a function from, say, the positive real line back to itself that is this return map, right? You give me a point on here, I look for the trajectory that it's on, and we follow it around, and the first place it comes back to, that's the value of my function. It's very easy to explain with a picture. I see virtually no computational content here. That's a warning sign, by the way. It's definitely a geometric definition on the face of it. So now, but these things, this return maps, they also exist for centers, except then it's not very interesting. If you're at a center, then nearby, you're just circles. You still have a return map, but it's going to be the identity. You start somewhere, you take a point on this transversal here, you follow it, you find the trajectory that it's on, and you follow it around, and what happens? The first place that I come back is where I started. So if you have a center, then this return map always exists, and it's just the identity. Now we have, say, this center focus thing, and now we've got a mixed bag. On some of the points, when we're on the circles, we're going to come back to where we started. So the return map will have a fixed point. But in between these fixed points, now we've got the spiraling stuff going on. So now we have the map again, sort of, since I'm going in this direction, it's advancing down this way, and I'll have it here. So the return map here, in this case, it could have fixed points going to the origin with non-fixed points in between them. That's possible. Now, the way to rule out a center focus is to make sure that from when you get close enough to the singularity, that either the return map is the identity, in which case you're a center, or it's there's no fixed points, in which case then it's a focus. That's the way you rule out, because you could think, because surely there must be some geometric way to tell when you're in one case and not the other. No, I mean, besides drawing the picture and looking at it, this is a sort of transcendental situation of some sort. So, in order for us to figure out whether our singularity is a center focus, or is it center or focus or center focus, we have to understand this return map. The behavior of that tells us everything. All right, in the analytic case, it's a far from a triviality. This is usually called Duloc's theorem, which I'm sure has probably come up elsewhere in these talks, and if not yet, it certainly will. Duloc's theorem says that if you have an analytic vector field, the return map is also analytic at the origin. By the way, I should say the return map is kind of trivially defined at the origin because it's a singular point, so it's a trajectory. So if you're there, you're there. It's always that's a fixed point for sure. So Duloc's theorem says that this return map is actually analytic at the origin. And now, so you extend to be analytic a little further on, and now you cannot have accumulation of fixed points by the identity theorem for analytic functions. If you have a sequence of fixed points going to the origin, then you have to be the identity by analyticity. And hence, you cannot have center focus in the analytic case. Okay. All right, so now instead of analytic, let's say we're C infinity and definable in a polynomially bounded minimal structure. All we have to do if we want to, so this idea that, well, everything in the analytic case should just go through, if we believe that, then basically what it looks like we're going to have to do is show that this return map is quasi-analytic, if you will. The return map has this property that you can't accumulate fixed points unless you're the identity. Yeah, okay, now that we just don't know how to do this. This is not easy. In fact, there were famous, I don't want to get into a history lesson at this point, but there was a flaw that went unnoticed for 70 years or something like this before people noticed it and tried to fix it. So this is not at all easy. Maybe that's not the hard, maybe that one's not the hard one. I'm not an expert on it. But what if we look at this, if we think about what we were just saying, the key point here actually is that somewhere to the right of the origin, that return map is behaving like, well, the return map is having the property that the fixed points either have to disappear or be everything. So there's another one. You say, okay, well, all we have to do is show that a germa, the return map, would be definable in some minimal structure. And then we could also rule out center focus. But we don't know how to do that either. So this is one of these things that you can run up against if you're not careful. In fact, forget the polynomially bounded C infinity and forget anything else. It seems pretty unlikely that you should wind up having a center focus in an O-minimal structure, period. And I actually think that the first person who ever mentioned this to me, I think was Lau, years and years ago. And he mentioned this problem, and I just thought it was so obvious somehow that you couldn't have these things. And it still seems like you shouldn't be able to have them at all. But the proofs of these things are notoriously slippery. And I think, again, part of the problem is that this whole notion of defining this return map, it's non-computational for the most part. It's an inherently geometric, yeah, sitting up on Mount Olympus, I could do that, sure. I'll figure out which trajectory I'm on, and then I'll follow it until I hit the line again. It's very hard to get your hands on this stuff. So this is an open question, just an O minimality, period. Can you have, and we'll keep it into the reasonable class. Can you have a C infinity vector field definable in a polynomially bounded O-minimal structure where the origin can be a center focus? So this is an open problem. It'd be great if anybody could figure out how to do it. But as far as we know, again, as far as we know, the only technology involves somehow using the return map and being able to say that you can't have infinitely many fixed points you can't have fixed points going down to the origin unless you're the identity. That's basically the only technology we know of to tell these apart, as far as I know. But other than that, I think other than ruling out a center focus, you pretty much can go through and say, okay, I can classify phase portraits of analytic vector fields pretty much like you can analytic ones, and the pictures will still be basically the same, except for this one. We don't know. All right. Questions, comments? Ooh. Let's get some clean surfaces here. I guess I don't really need this now. I think that picture was good enough. And this return map technology, I mean, this does have analogs in higher dimensions as well. But remember, for now, we've got enough. Our hands are full dealing with planar polynomial, with planar definable vector fields. So we'll stick with that for now. Okay, so let me also mention one other. I'd like to also just mention another case where non-trivial results about analytic vector fields can in fact be just modified to hold for polynomially bounded O-minimal ones. So this is something that is in arbitrary number of this started off being called the Gradient Conjecture, although it's no longer a conjecture because it's a theorem. But now a theorem. So I don't know what we call it these days because the names involved. Now a theorem due to, let's see, so this is Kurtica, Masowski, and at least the version I know, Karshinsky. There's a symbol here that I can never remember where it goes. I think it's there, maybe. Okay. So this is a theorem it was done around 2000. So the original conjecture was that, so you have an analytic vector field. Oh, sorry. You have an analytic function of, say, n variables, arbitrary number of variables, real analytic. And then you're going to look at the gradient now. Now, this is basically going from subsets of Rn, say, into Rn. And so you think of this now as a vector field. Okay, so you started with an analytic function. It's analytic, at least in the neighborhood of the origin. I'm just being lazy with the notation. So this now is a special kind of vector field. It's a gradient vector field of an analytic function. And say you have an isolated zero. A singular point, isolated singular point at the origin. And the conjecture, and so then a trajectory going to the origin, say a gamma trajectory going to, or coming out of, either way, going to zero. And the conjecture was that, well, there's actually a bunch of conjectures with it. The weakest one is just that the limit of the tangents of the secants exists. So I guess I'm parameterizing probably as we go to infinity, so let's do it that way. The limit as t goes to zero of gamma of t over the norm of gamma of t exists. So I think this is the easiest way to state this. So these are secants, right? You're measuring you're measuring the angles basically as you go in. So this was a conjecture that was open for quite a long time, and it was solved by these guys. It was published in 2000 in Annals of Math. So I mean, it's a serious result. There's lots of there are also a lot of stronger versions of this that actually turn out to still be open because, okay, well, that's great, but what about, how about this guy? I think this is still open in general, although it's known in some special cases. This is sort of an indication that we should be looking at some sort of minimal phenomenon or something here, right? We're pretty sure that when you have a gradient vector field and you have a trajectory going in there, it should calm down. It certainly should not oscillate back and forth across any analytic or subanalytic sets. And the idea is that this trajectory, we could look at this and think this trajectory should probably be minimal. But as in this generality, as far as I know, and I'd love to be corrected if this has changed, but only this version holds so far, as far as I know. This one we don't know. Open, I think, in general. Open in general. I do know there's some special cases where this works. Let's see, what is it? If n is 3 and f is harmonic, then I think everything is known there. But okay. So here's a result that's about analytic functions, and it's a reasonably complicated proof. So here is something that's nice about this, however. This actually goes through. This works for C infinity and definable in a polynomially bounded O minimal. So here's one where you really can, and now there's work that needs to be done, and in fact, you need to rely on other work that Kurtica did a nice result about a sort of abstract way of Savage inequality that works in arbitrary O-minimal structures. So a lot of times you can carry out these programs. This is one of them. You will not find this published, but one of the reasons why I want to bring this up is to once again try to make everybody aware of how important Fields Institute has been in this whole game, because the reason where this was checked here at the Institute several years ago in a little mini workshop that we had upstairs, where people just showed up and we checked it all. Kobe was here, I think. You were here for this, I think. So this has never been published anywhere, but we all got up there in the library, I think it was, and just hashed this all out and checked everything. And here you can generalize the technology so that this works here. And then you can ask the same questions. Here we go again. Trajectory, now living in 3 space. Now we don't have Pfaffian technology available. And as nice as these things are, and they are, gradient vector fields are very special. They have we should know this from calculus, that there are special things about gradients. Even knowing all of this, this is, as far as I know, the best that we have. This is certainly not enough to guarantee Pfaffian, or even if it was. So even going to 3 space, even looking at something like this, we're still kind of at a loss for what to say. So even though all of this stuff also works for the C infinity case, blah, 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 which is the field of exponents Q, all of that stuff, we still are stuck when we try to leave the plane, even when we have a lot of information.
But this said in the fundamental alternative in the plane, you say the gradient vector field will never have a spiral.
That is correct.
In an alternative way.
Sorry, wait a minute. Here, C infinity.
Yeah, even C infinity.
Yeah.
No.
Yeah, gradient vector fields can't have spirals. There's something tingling in my memory that Sergey did something about that, and I can't remember what it is. But I gather that he's around.
He was wrong.
Well, okay. Well, we'll yeah. But it's so long ago. He was here too, I think. So anyway, so here we are. We're all at Fields again. Maybe we can all work together and try to push things a little bit further. But here's an example. This is an example where one of these proofs that was just given in the analytic case really can be pushed through for C infinity and definable and polynomially bounded O-minimal, and without a whole lot of work. That's why it was never published, because really it was like, okay, you go have a mini workshop and go through and check the proof. And once you know enough about O-minimal structures, you can just crank through it and say, oh yeah, okay, everything works fine. So you won't find this published anywhere, but it is a fact, and it was established here. So there's some good culture. Okay, I think I'm supposed to go to 10:50, but now what I'm going to do is I'm going to pull the stunt of saying, does anybody have any questions or comments? Because if not, I think we're done. Well, yes, if not, we're done. Questions, comments, updates. I'd sure like to know if anything has changed here, but I don't think so. Okay, we'll see you Monday with more mysteries and fun and hopefully more pictures.